is Suhaib Mahmood, and today I'm going to be going over the Nanotechnology and Magnetism mini lesson. So because this is a mini lesson, make sure you leave time after the lesson is over for the students to ask questions and whatnot. So quick review, or quick questions you want to ask the students and kind of like give them some background information about this lesson is like, what is magnetism? There are south poles and north poles and opposites. There are two types of magnetic fields, north poles and south poles. Opposites attract and like poles repel one another. The Earth's core is also magnetic because of the iron and nickel that is inside of it. And a fun little fact that you can tell your students is the reason that your blood is not magnetized because of the iron in it is because there is a protein that holds onto it. So the first experiment is going to be a little bit of a demonstration of the south and north poles in magnets. So you're going to go and give both of these things to a group of 4 students and then break them up into pairs. One pair is going to have the magic magnetic wands, and the other pair is going to have this. So the point of the magic wands is, so one side is north, one side is south. As you can see here, they are labeled and they attract. But if you flip it, they repel one another. So that's something cool for the students to just kind of play around with and experiment with. This over here, that the other group is going to be dealing with, has the same idea. There's a north pole and a south pole on these like little magnets, and this itself has the south pole pointing up. So if you have the south pole pointing down, it floats, and you just kind of keep building it. And there you go. Make sure they don't do this because it will launch the magnets, and that's not what we want. It might create a mess. So yeah, then have the guys, the pair change. And the group that was working with the wands is now going to work with the tower, and the group that was working with the tower is now going to work with the wands. Alright, so this next lesson introduces the concept of permanent magnets versus temporary magnets. The magic wands we were working with earlier are permanent magnets in that they are always magnetic. Now, a temporary magnet is something that's not normally magnetic, as you can demonstrate with these paper clips here. Show it to the students. They don't at all attract each other. But if you put the paper clip on the magnet and then put the paper clip touching the magnet to another paper clip, it becomes magnetic. And then you can just kind of keep building a chain, see how long you can get it. And you can explain this happens through the process of induction, where the permanent magnet will realign the magnetic field of these temporary magnets to make them magnetic, but obviously it only lasts while they're in direct contact. You can show again that once the magnet has been removed from the paper clips, they no longer attract one another. Alright, so the students should have this handout over here, which you can use to explain what's going on with the paper clips. An object that is magnetic has its poles aligned in this fashion. An object that can be magnetic and is in an induced magnetic field, the temporary magnet, will also have this alignment. Now this is what a magnetic material that could be an induced magnet but is not in a magnetic field looks like. So as you can see, when the paper clips were influenced by the magnet, they went from this to this. And a material that is not magnetic and can't be magnetized has this sort of magnetic field. It just doesn't. Now we're going to introduce the concept of magnetic fields. Up to this point, they've kind of been invisible to the students, so now we're going to show a way to visualize them. You take this petri dish of iron fillings and you stick the magnet underneath it. And you can see the magnetic field lines coming out of a visual representation of the magnetic field lines coming out onto the iron oxide fillings from the magnet. And now you bring in another magnet into play, lodestone. It is a slightly weak, it's kind of a weak magnet, so you really have to look closely, but you can see that the iron fillings are moving a little bit. And here you're going to ask the students about some like differences between like what's a permanent magnet and which ones are temporary, like classifications. So both the lodestone and the magnetic wand are permanent magnets, and the temporary magnet, an example of that would be the paper clips. And another thing actually over here, the iron fillings themselves are temporary magnets. As you can see, once the magnet is induced, they all kind of like clump together. Actually, something cool to tell the students is that the iron fillings in here and the iron in the lodestone are actually both Fe3O4, and so they're the same material. And we're going to get into why that, or we're going to get into something a little interesting in a bit. To further demonstrate the concept of magnetic fields, we're going to play with this iron oxide powder, which is the same stuff as the fillings, just in powder form, and then the iron oxide in solution. So if you put the magnet here, you can see it has the same effect. You can see the little magnetic field lines. Same thing with the powder. If it's a little bit hard to see on the inside, what you can do, you can see it right now, but what you can do is you can just kind of hit it on the table and have the powder kind of fall off the walls and settle to the bottom. Up to this point, we've shown the magnetic field in just one dimension. So now we're going to demonstrate the concept that magnetic field strength goes in 3 dimensions, and we do this using this. So look at that. You can see that magnetic field lines go in all 3 directions. Alright, so now we're going to start incorporating nanotechnology into this magnetism lesson. First, make sure the students know what nanotech is and what the significance of it is. So macroscale objects are everyday objects. Here are some examples. Microscale, like blood, germs, all these cool things. And then nanoscale is even smaller than that, and it's like DNA strands and buckyballs. Really cool stuff. And then something else you can use to demonstrate how small nanoscale is using this how big is your hand test. It's going to be a handout for the students. So I'm 18 centimeters, that's 180 million nanometers. Now we're going to work with something called ferrofluid. This is the same iron oxide powder we were working with earlier, but it is now on the nanoscale. And as you can see here, it's going to have slightly different properties. Look at that. It's almost in solution form, and it has the properties of the magnetic solid, and at the same time it has the properties of a solution or a liquid, which is really cool, and it's only possible at the nanoscale because the particles are super, super small. Fun thing for people that are teaching this lesson, not something that the kids would understand, but every element on the periodic table, once the atom itself becomes smaller than the probability region of finding the electron, so the orbital, it starts exhibiting quantum confined behavior, and basically every element on the periodic table is going to behave differently when it's on the nanoscale.